Assalamu alaikum guys. Here is the second lecture of design of beam column. So here for the lecture number 2, contents we will discuss first. First of all, we will discuss in this lecture about the movement adjustment factors, CMX or CMY. Then we will discuss about the K value for the frame beam columns. Then the movement magnification factors, beta factors. Then the selection of the trial beam column, and finally the flow chart for the design of the beam column. So at the end of this lecture, you will be able to start with the design of any beam column, and we will be able to discuss about or going. So starting with the first content of today's lecture, that is the movement adjustment factor, CMX or CMY. So from the subscript, it will be obvious. This X is mean the movement in X direction and Y mean the movement in Y direction. For the restrained compression members in frames braced against the joint translation, mean no side sway. If your joint is braced against the translation motion, mean translation movement, then we are going to be say it as no side sway. And it not subjected to the transverse loading between there the support, then the equation to find out the CM is given over here, that is 0.6 minus 0.4 M1 over M2. What is M1? M1 is the smaller end movement and M2 is the larger end movements. Okay, so it may be top end movement, it may be bottom end movement. Any one of out of M1 and M2 may be top end and may be bottom end. But only the difference between M1 and M2 is the one subscript is going to be represent the smaller end movements, and M2 is going to be represent the larger end movements. Okay, so here this M1 over M2, the ratio of M1 over M2 is very important. If your ratio of M1 over M2, depending upon the direction of the forces, it comes out to be positive. Okay, it will be positive. You are going to be designate the ratio value. Okay, the numeric value you are getting by subtracting the only the value of M1 and M2. It comes out to be positive. You are considering it at positive for using in this particular equation when the member is bent in reverse curvature, and it is negative when the member is bent in single curvature. You can see in the figure what reverse curvature is and what single curvature is. In figure A, you can see that if the direction of the movement, end movements and the bottom movements, mean top movement and bottom movement, if the direction of both of these movements are same, it is clockwise and it is also clockwise. So if this is the particular case, then you are going to be see the curvature, the bending curvature of this column, it will be like this. So it is going to give you a reverse curvature, and your reverse curvature is going to give you the positive M1 over M2 answer. And if you have the single curvature, what does it means? The opposite direction of the movements at top end and bottom end. So at top it will be in counterclockwise, let's suppose. So here bottom it will be clockwise. So if the opposite direction of the movements be there at top and bottom of the column, it is going to give you a single curvature, and the value is taken as negative. Okay, so this you have to be very careful while calculating this equation for CM, that rest of the values will remain same. Okay, and this equation you are using the conditions you have to keep in your mind, that the restrained compression members in frames, those are braced against the joint translation, mean no sway condition, no side sway, and it not subjected to the transverse loading between their supports in the plane of the bending, mean if it is going to be restrained. So what does it means? That at top and bottom you have a proper supports, it may be hinge, it may be fixed, but in between also the no lateral loads has been applied, extra loads are not going to be applied in transverse direction. So transverse loading is not applied between the supports. Now next is when transverse load is applied between the supports, but sway is prevented. So your CM is conservatively taken equal to 1. Okay, so if the loads are applied, even the joints are restrained, no side sway condition, but along with that, second condition has been changed, that your transverse load is applied between the support. Okay, so your sway is prevented. So what you have to do, your CM is conservatively taken equal to 1. Otherwise, in such cases, CM may be approximated. So if you are not interested to take the conservative value of the 1, then what you can do, you can use the proper equation, the different equation for the case when the transverse loads are applied for the restrained ends. Mean the end conditions are no sway, but the in between of the column, the lateral loads has been applied. So for this particular case, this equation is used to calculate the Cm. That will be 1 plus psi alpha PR over PE1, where alpha is 1 in LRFT and 1.60 in AST. You have to keep this in your mind. And how the psi is going to be calculated, that is by pi square delta nod EI over m nod L square minus 1. So delta nod is the maximum deflection due to transverse loading, and m nod is the maximum first order movement within the member due to transverse loading. So those will be your given data, and you can input over here and you can get your answer for the psi. And this psi is needed to be input in this equation. Alpha PR over PE1. PE1 will be the elastic critical buckling load due to the first order effect, and those will be given to you, and all of the values will be with you, and you can calculate it very easily by using Idler critical buckling load or the formula to calculate the Idler elastic critical buckling load. Next content of this lecture is the K values for the frame beam columns. How to get that? The K values for the frame columns with partially fixed ends should be evaluated using the alignment charts given in reference number 1. So we have discussed in the online session that how to get those values, okay? And also when we are going to be solve the numerical problem, we will discuss over there. So in the reference book, our LRFD manual, actually reference 1 is LRFD manual, there the alignment charts are given. So once the top end and the bottom end, K values, psi values will be with you. We are going to be calculating the G or the psi values, and if it is going to be incorporating, and we are going to be aligned right and left part between top and bottom conditions. And finally the in between chart, you are getting this kind of the chart in LRFD manual, okay? So here you have the K value for your column. So here you have the GA, and here you have the GB, mean the top end conditions and the bottom end conditions. So the stiffness is involved over there. So depending upon the moment of inertia of the column and at top end and bottom ends, and there also the connecting elements on that particular ends, top end and bottom ends, you are calculating the G and GB. And these formulae to calculate the G and GB are written in the LRFD manual. So here you have the different scales of the values, and here you have the different scales of the value. So once you have been calculating the GA, this value is going to be marked on the scale of this chart, and GB is calculating it, its value can also be marked over here, and you are going to be join with a straight line the GA and GB value, and wherever it is intersecting the intermediate K column, that chart, that value, this is also going to be marked or the scaled with a certain values. So that K value will be the value of your column, particular column. So however, if details of the joining members are not given, so here to use these alignment charts, to calculate the G and GB, all of the informations will be given. If those informations of the connecting elements, members or the joining members are not given, then you have to follow the approximate estimates. Mean the K can be used any value between 1.2 to 1.5 if side sway is permitted with partially fixed ends, and K you can use is equal to 1 if side sway is prevented but end conditions are not mentioned, okay? So side sway is permitted, mean to say that you are allowing the movement to be moved, so and ends will be the partially fixed ends, and side sway is prevented, mean no sway condition, so but end conditions are not mentioned. So in this case you can use K is equal to 1 directly. Then comes movement magnification factors. That's what factors in lecture number 1 we have been discussing as in multipliers. That you are using or doing the analysis, a simple first order elastic analysis for the column, and whatever the results you are getting, you are using a multipliers, and you are multiplying with the results of those to get the movement magnification. Magnification means the second order effects. This magnification, movement magnification effects are going to be to incorporate the second order effects to get the beam column analysis. So your movement magnification factors will be B1 and B2, are used to empirically estimate the magnification produced in the column movements due to second order effects. These are separately calculated for sway or the lateral translational case, and for the no sway or the no translation case, NT case. So wherever you will see the small n and small t case, it's mean that it is no translation case. What does it means? In other way, it will be no sway. your joints of the column, ends of the column are properly restrained, or your column is properly braced. And if the lateral translation case is there, mean LT, small l and t is written. So what does it mean? That it is lateral translation case, mean the sway conditions are there. So sway mean that your column is allowed to sway in lateral direction due to the applied forces, axial forces, or the eccentricities. So in this particular case, you are getting the structural effects and the member effect, that what we have been discussing in lecture number 1. So your member effect within the column is incorporating by using NT case, and your structural effect is going to be incorporating by using the lateral translation case. Then finally you are getting the B1 and B2, and you are superimposing, or you are just taking the combined effect of both member and structure effect, and to get the moment magnification, the final second order effect. According to the frame, accordingly, the frame is to be separately analyzed for the loads producing the sway and the not producing sway. And this will be more clear to you once we are going to be solve the numerical problem, and you are going to be solve your own design problem in which you are using the frame analysis with the no sway condition and the sway condition. And separately the moments is needed to be calculated and needed to be multiplied with B1 and B2. Now, if this is the particular case, then we have the different terminologies used during the beam column analysis. So, for this moment magnification factors, we are going to be used for the movement with subscript LT, MLT, that is going to represent the movement due to the lateral loads producing appreciable lateral translation. Then you have a B2, so mean corresponding to LT, the lateral translation case, the subscript 2 is going to be used. 2 mean LT, the moment magnification factor to take care of PU delta effect, the structural effect for sway and deflections due to the lateral loads. Then comes MNT. So for the moments you are writing in subscript NT, that is corresponds to the moment resulting from the gravity loads, not producing the appreciable lateral translation, the member effect. And B1 corresponding to that moment, the multiplier is used, that is B1. That 1 is going to be represent the no sway condition, NT condition. So moment magnification factor to take care of PU delta effect, the member effects for no translation case. And finally, how to get the MR, the numerator of the interaction curve, that is the required magnified flexure strength for the second order effects, and that can be get by using by superimposing the effect for the second order effect by superimposing the member effect and the structure effect. So member effect means the B1, okay, into MNT no sway condition, and the member effect is the structural effect is due to the sway condition, B2 MLT. So whatever the moments you are getting for no sway condition needed to be multiplied with the B1 to get the second order effect, to magnify the moments, and MLT is needed to be multiplied with B2 to magnify the moments. So magnified flexural strength for the second order effect is we can get very easily. Okay, so in this way we are following that approach to solve or to design to do the analysis of the beam column, in which we are calculating the simple movements for the sway and no sway conditions and using the multiplier to magnify it. PR is the required magnified axial strength. So required axial strength is going to be having a PNT plus B2 PLT. So here we are not having the B1 multiplying with PNT. Why is that so? Because your PNT is already the axial load, that is the gravity load, that is not causing the sway. So what does it mean? That there is no need of the magnifier, because the member effect is due to the axial load. So your axial load itself is causing the bending moment. Okay, that is going to be give you a certain P delta effect. So your P is causing the P delta effect. So what does it mean? Itself P is not required the magnification for the gravity loads, but the lateral loads are always required the magnifications, because those are going to be needed to be magnified, because for the second order effects those are going to be enhanced, their effect is going to be enhanced. So that is going to be incorporated by multiplying it with the multiplier, that is P2. Now next step is that how to calculate those magnifiers. multipliers आप कह सकते हैं, B1 and B2. So B1 is going to be calculated by using this equation, Cm over 1 minus alpha PR over P1, and its value should be greater than or equal to 1 because it is a multiplier. Okay, so at least it should give a 1 value or more than that. If its value comes out to be less than 1, you have to keep at least equal to 1. Okay, so less than 1 doesn't matter, it is going to reduce actual producing moment, so we are not requiring that. So if your B1 comes out to be less than 1, you have to take it at least equal to 1. More than 1 is okay, any value more than 1 you can use. So where in this equation alpha is equal to 1 in LRFT and 1.60 in AST. And PE1, as I have told you earlier, it is the idler buckling strength of the braced frame. And its formula is well familiar to you. It is pi square EI over K1L whole square. So K1 is the effective length factor in the plane of the bending for no lateral translation case. That you have to keep in your mind. Wherever the B1 is there, so mean 1 is going to be going to correspond or going to relate with the no sway condition. So all of the 1 subscript is going to show you the no sway condition. So that will be equal to 1 or any smaller value by the detailed analysis. So conservatively you can take it as 1. So for the sway magnification, we have to calculate B2 multiplier. That factor magnification, that is also called as sway magnification factor. So it can be determined from one of the following formula. So one formula is given over here in this slide. That is 1 over 1 minus alpha sigma PNT over sigma PE2. So here alpha is equal to 1, same in LRFT and 1.60 in AST. Sigma PNT, it is the total vertical load supported by the story. So if you have a one story in which one beam column is needed to be designed and going to be analyzed for B2. So for that particular case, you are going to be using the going to be calculate the total vertical load that is supported by the whole of the story. So instead of the one beam column, and then you have to count the number of the columns, and on all of the columns, whatever then the vertical loads be there, you have to add it up. So this total value will give you the sigma PNT. And sigma PE2, this is the measure of the lateral stiffness of the structure. Okay, so if PE2 is required to be calculated, so for the second order effects, for the sway magnification, the simple idler critical buckling load is not required to be calculated. The same formula you cannot use. You have to incorporate the different other factors or the parameters. So this measure of the lateral stiffness in sway condition, the lateral conditions be there, so the lateral stiffness is needed to be required to be incorporated over here. So for this, the formula is R M sigma HL over delta H. So what are these parameters? One by one we will discuss. Here in denominator delta H is written. It is the story drift from the first order analysis due to the lateral load capital H. Okay, so story drift is very simple. If you have a column and it is going to be giving you a certain delta value with respect to the H. Okay, so and you are getting the delta H. Okay, so you have the drift value. Delta H is story drift. Story drift mean the lateral deflection. Okay, so lateral direction deflection due to the applied lateral loads. Okay, so this lateral loads may be capital H. So if on the columns in sway conditions, the lateral loads has been applied, so the certain lateral deflections has been produced. So this is going to be called as delta H. RM is 0.85 for the moment frame and 1 for the braced frame. So whatever the case is, you are going to be use the corresponding values. Now, it is often desirable to limit the lateral displacement. This lateral displacement delta H, you cannot use randomly any value. For the safe design, we need to be restrict or limit the lateral displacement or drift of a structure during the design phases. This limit can be defined using a drift index, which is the story drift divided by the story height. So in which story you are, here you have the columns, here you have the story height, and then further you have the column is continuing within different stories. So whatever the story height is, that may be capital L. So this story, the lateral load, the story drift divided by the story height. So it will be going to give you the drift index. The design then proceed by selecting the members so that the final structure perform as desired. This is similar to the beam design where deflection in the serviceability criteria we are going to be used, because a drift index can be established without knowing the member sizes. So it can be used in equation number 2. Thus analysis with assumed member sizes is unnecessary. So if we are going to be apply the limit on the drift index, then in this particular equation the PE2 is formula is not going to be incorporating the dimensions like PE1 formula, ideal critical buckling formula. So there we requiring the I value. So to calculate the moment of inertia, the member sizes are important to know. So if you are going to be do the design, so for the design you are not, sometimes you are not familiar, you are known, and it is obvious that you are not known with the member sizes at start. So if at start the member sizes are not known, so it, by using this formula it becomes unnecessary. Okay, so you can use this equation number 2 when the particular design sizes are the element or the member size are not known to you for the design phase. But if let's suppose if it is restricted that this sizes is anyhow is going to be used, and we have to justify our design procedure and analysis values on that particular design or the member sizes, then you can use this equation number 3. This equation number 3 is going to be incorporating the B2 equation, incorporating this PE2. Okay, so finally you have 1 over 1 minus alpha sigma P and T over sigma PE2. This sigma PE2 can be replaced by this equation R m sigma HL over delta H. So here you can modify it. So we have discussed the value of alpha and sigma P and T. Rest also we have been discussed. So just you have the values you can input over here. Here sigma H mean all of the lateral loads applied in that particular story where the beam column is needed to be designed under consideration, and capital L is the story height. So in the last slide, whatever I have told you, that if the column sizes of the structure are known, okay, so before calculating the sway magnification factor, then you can calculate your B2 by using in the same equation, but the PE2 formula can be replaced by sigma pi square EI over K2L, where I and K2 is calculated in the plane of the bending for the unbraced conditions, means sway conditions. If it will be braced, it will be no sway. So for the sway condition, if 2 is there, so it always be unbraced condition. For the comfort of the occupant, okay, here in steric, the value is written, that is from slide number 10, where the drift index we were been discussing. So drift index is the ratio of the drift to the story height, okay, delta H. Drift index is the ratio of delta H, mean drift divided by story height L. So this drift index value, as I have told you, that must be in a reasonable limit. So that limits is defined for the drift index for the working at working loads to the value of 0.0015 to 0.003 and about 0.004 at ultimate loads. So before using this drift value, we have to be ensure with the drift index, mean we have to limit this drift value by using this drift index value, and if it will be within the limits, then we can use in the equation delta. Mean to use in the equation given in slide number 10, the delta H can be calculated first deciding any value of drift index. Once it will be decided that the drift index we are taking as 0.004, we are service load design we are doing, and that is at ultimate loads. Okay, so for ultimate loads the service design is involved. So for the service design we are taking as the value 0.004. So we are multiplying our index, drift index 0.004 with the story height. So it is going to give you the drift value, mean delta H, and that delta H is going to be used in the equation given in slide number 10. So this part, the steric part, is for slide number 10 particularly. So it's nothing to do with this equation. Now next is the selection of trial beam column section. So only one problem is there. Once you are there to trial to use the beam column section, that whether to use your or to select the trial section based on the bending stress, mean beam, or as a column by considering the axial stresses. This is the only problem that we have to be sorted out. Okay, So the only way by which the interaction of axial compression and the bending moment can be considered is to satisfy the interaction equation. That is very important. You have to note it down with you, okay, that whether you are considering selecting your trial section for the beam column based on beam or column, whatever the case is, finally you have to satisfy the interaction equation, okay. That is going to give you the superimposed effect of the axial stresses and the bending stresses. However, in order to satisfy these equations, a trial section is needed, okay. If you want to satisfy the interaction equation, then this design interaction equation needs a trial section. For this trial section, maximum axial compressive strength and the bending strengths may be determined. So we already be having the MU and PU with us after the load analysis of the structure. The difficulty in selection of a trial section for a beam column is that whether it is selected based on area of the cross section, mean the axial stresses, or the section modulus, mean the bending stresses. No direct method is available to calculate the required value of the area and the section modulus simultaneously at one time. For selection of the trial section, the beam column, it's very important. Conclusion is that the IISc specification also says that, so how we can solve this problem, that we can select our beam column temporarily changing into a pure column, purely axially loaded column, and then by approximately converting the effect of the bending moment into an equivalent axial load. If you have the axial load with you, so what you can do, you can add into it the bending moments that is going to be approximately converted into an equivalent axial load. You mean your bending moments are converting or going to be transformed into an equivalent compressive axial load, and finally you can get your PR, okay. That can be used for the selection of your trial section. Sorry guys, in slide number 12, the last point I have told you that after getting the equivalent by converting your moments, bending moments, in an equivalent axial load and your actual axial load applied on the column, summing it up, you are getting the P equivalent, not PR, okay. PR is the design value, that is not going to be used over here. This is P equivalent. So P equivalent mean that at the start you are converting your moment. This is other than the magnification, okay. So we are not doing the magnification over here, just we are taking converting our moments into an equivalent axial load, so that at the start we can take the trial section. This P equivalent is to consider your column as an pure axially loaded column, so that you can consider or you can take your trial section based on the cross-sectional area, or considering it as an axially loaded member. So for that particular case, we need the P equivalent, okay. So for this P equivalent, you need a certain factor that is needed to be multiplied with the movement, so that you can get the equivalent axial loads, okay. Your movements are going to be converting into an equivalent axial load, and in x direction and in y direction. This factor is going to be called as mx for the mrx, mean for the movements in x direction, and my for the movement in y direction. For the very first trial, the equations to get the mx and my are 8.5 minus 0.7 k1 lx and 117 for my, 17 minus 1.4 k1 y into ly. So you can see only the length of the member are the information required to use these equations for the first trial, and the effective length factors are required over here. So these are not going to be including the member sizes. So it will be very easier to use and convenient to use these equations for the first trial. Once in the first trial, you are getting your mx and my, you can go towards this equation. The answers of these two equations you can input, and you can get your PR. And finally, you can get another trial section, okay. If your PR is same to that, mean the K by Ly equivalent are coming equal. If not, then you are going to be calculating your mx and my by using these set of equations. For the next trials, further trials, after the first trial, second, third, fourth, fifth, and so on, you are going to be use these set of equations to calculating mx and my. This is 10 minus 14 d by 1000 2 and rest will be the same 0.7 k1x. So first parameter is going to be modified as 10 minus 14 d by 1000 divided by 2. So here you can see the depth of the member is incorporating, size are incorporating. So it means that once first trial section will be with you, so its depth will be now logical and practically be with you. So that member sizes you can use in the second for the second trial, third and fourth trial. The above equation is evaluated for the P equivalent and a column section is selected from the concentrically loaded column tablet tables for that particular load. The equation for the P equivalent is solved again using a revised value of the M. And the section is selected and checks are then applied for this trial. So what does it mean that whatever the section you are getting by using this set of equation for the first trial are not the final one. Okay, so once the section will be with you, that D you are using to calculate mx and my, and again you are calculating P equivalent, and corresponding to that P equivalent 2 the second time you are getting another trial section. For that you are going to be applying the checks and later on so on. So the last content of today's lecture, this lecture number 2, is the flow chart for design of the beam column. This flow chart, the very first step is the known data, input data. That should be PU. By the load analysis you will get PU. By the load analysis you will get MNTX. For the no sway conditions you will get MLTX, the movement for the sway condition. For the frame, steel frame, and MNTY in Y direction no sway conditions, in Y direction sway conditions, mean for the sway condition the movements Kx, Lx and Ky, Ly for the stiffness calculation. And then you have to calculate, the second step is after calculating Pu, you have to calculate Mu. Mu will be MNT plus MLT. Separately you have to do the load analysis for the no sway condition for the frame and the sway condition for the frame, and then you are getting Mu. You have to calculate MR for both X and Y directions if it is required. If it is not required, then only one direction will be sufficient. Next is you have to assume an approximate magnification of 15% for the movements only. At the start, before applying the magnification factors, just for the safety, it is recommended. If one designer or any consultant engineer is not required to use this 15% magnification, then it will be okay. But majority of the designers are suggest that if at the start if you are going to be used 15% magnification, then at a later stages it is going to be reduced to your trials. Okay. Even using this 15% magnification, the magnification factors are still needed to be required to be used, B1 and B2. So your P equivalent will be PR into MRX. So here if you are incorporating this particular point, then it will be 1.5 MRX and into MX, and here it will be 1.5 MRY into MY if you are using this particular point. If not, then the simple equation is used. So it's up to you. So the next step we have discussed earlier, that you have to calculate mx and my for the first trial, then mx and my for the second, third and so on. Next is to select a section as a simple column depending upon the following criteria. So these 4 criteria should be satisfied for your trial section. That the first one is obvious, your area selected should be approximately equal to area required. But the second one is the weight should be minimum. Out of all of the area selected, those are very closer to the area required, you have to take out the section having the minimum weight. Then connecting length B should be greater than B minimum, and depth of the section should be less than or equal to 360 millimeter. That is by the AISC specification specified that the depth of the section for the beam column is considered as less than or equal to 360. Next is the column selection tables may also be employed to select the section using the values of the P equivalent and Ky, Ly. Okay, so in the last slide we have said that the beam section you are selecting. So here you can select the column selection table. So you have, for that you have to calculate P equivalent and Ky, Ly, and corresponding to that you can enter within the tables, and you can see the Rx and Ry from the column selection table for the selected section. This Rx and Ry you can use to calculate Ky, Ly equivalent. The Kx, Lx of the column itself divided by Rx over Ry of the selected section, and re-enter the table for the greater Ky, Ly and Ky, Ly equivalent, and then revise to obtain the suitable section for the load P equivalent. So once it is going to be stabilized your values, when you are getting the same answer, so you can use this for your trial section. So find the new value of the M for the subsequent trials. Select a new section and repeat until values of the load capacities P equivalent and M are stabilized. So your P equivalent you can use by using this formula. So what does it mean? This step shows that you are not going to be start by using the next procedure to apply the moment magnification factors to calculating the CMX and CMY. First, what you have to do, you have to stabilize the P equivalent value, mean the trial section you have to stabilize. What you can do, you can make a table. That is going to make your calculations very convenient. The first column can give you the number of trials. So number 1, number 2, and so on. Okay, so I'm adding another one, number 3, let's suppose. I'm explaining you this stabilizing, what does it means. So here, what was the first step? That you have at very start, you do not have the value, mean you have only the P equivalent. First of all, you have the P equivalent. You are calculating based on the mx and my for the first trial equation we have discussed in the last slide, first trial. Okay, so you have calculated P equivalent. So corresponding to that P equivalent, you have in the next column, let's suppose you have a trial section. And in next column you can write M X, and in the next you can write My. Okay, so whatever for the first trial you have calculated, from that you have calculated P equivalent and you can enter in this trial and error table. Okay, so for the number of trials, for the first trial you have certain value of the P equivalent, and depending upon this P equivalent you enter into the table and you get one W section. Okay, so anyone you may have multiplied by this. Okay, so keeping this W section, its properties means D value, you have the second set of the equations to calculate Mx and My. Okay, so for the second and onward trials, so from there you are calculating Mx and My. Okay, so you have one value of P equivalent and you have one value of Mx and My for this trial section. Now what you can do, you can use this Mx and My to calculate another P equivalent for the second trial. Okay, you can again enter into the table, you can select the second section W. Using its depth, you can calculate another Mx and another My. Using this second trial Mx and My, you can calculate another P equivalent, and based on this P equivalent you are selecting another trial, and using its depth you are calculating another Mx and another My. Okay, so now let's suppose you have 4 values, 5 values, you have done this trial and error for 4 times, 5 times, 6 times and 7 times. So what is happening with the values of P equivalent and with the values of Mx and My? Those are fluctuating. Here you are getting a P equivalent, let's suppose 2000. Here you are getting 3000. Here you are getting, let's suppose 5000. So fluctuation mean The difference between two consecutive values here is 1000. The difference between other two consecutive values are 2000. And maybe the difference between the other two values be more than that or less than that. Okay. So if the difference between any two consecutive trials are becoming stabilized, mean reduced, or almost equal p equivalents you are getting for any two consecutive trials, that is going to be stabilize your value. Either of p equivalent or mx and my. You have to keep an eye on the values of column of mx and column of p equivalent on both of the columns. Either of mx, my or p equivalent. Anyone if it is going to be stabilized, meaning the difference between any two consecutive values, it will be very less, then you can say that it will be your final stabilized value for the p equivalent. Okay, so in this way you have to go towards the stabilization. Stabilization mean the error you have to reduce between the two consecutive values. So anyone, it may be 6th trial or 7th trial, that is going to give you the p equivalent value with a very lesser difference. Okay, so it may happen that first the difference between the two consecutive values are reducing, and then suddenly after this any one of the trial, like 7th trial, if you are doing the 8th trial, here it is the difference for the 6th and 7th is reduced, but between 7 and 8 it is again start increasing. So what does it mean? The 6 and 7 is the final value. So you have to be decide it depending upon the difference between two consecutive values. So this stabilization is very important. So this you have to do. And better is to make a table that is going to be make convenient your calculations to stabilize the p equivalent and m. So wherever it is going to be stabilized, that particular p equivalent, section will be the final section to start with the next step of the flow chart. Select a new section and repeat until values of the load capacities p equivalent and m will be stabilized. That's what I am talking about. Now, next step is to calculate CMX and CMY for no sway conditions. For that, you need to calculate you have to check for the R value. If your capital R value, slenderness ratio comes out to be less than equal to 200, then it will be okay. After the check of the slenderness ratio, you have to go towards the CMX and CMY calculation. So axial strength of the trial section. Axial strength of the trial section, calculate phi CFCR corresponding to R value that in the last step we have been calculating, or directly read it from the table in reference 1 LRFT manual and evaluate the compression capacity by multiplying it with the area. That is very well familiar procedure for any compression member. So phi CPN will be phi CFCR AG over 1000 and you are getting that. Next step is you have to calculate the idler buckling strength for the no sway case and for the sway cases, PE1X, PE1Y, PE2X, PE2Y for both LT and NT. So PE1, the formula is already familiar, you can use this formula. So for the next slide, you have to calculate B1X for no sway condition, B1Y. You have already CMX calculated in the later steps, and now you have the equations as we have been discussing earlier. So you can use it. So its value I have told you should be greater than equal to 1. If it comes out to be less than 1, so you have to consider it equal to 1, at least equal to 1 for both. So a PR in the above formula is the actual factored axial load, not the P equivalent. That is very important. Okay, so P equivalent concept is just for the trial section. Once the trial section is with you, so forget about it. So this PR and P equivalent are two different things. That's what I have told you. Calculate B2 and B2I for sway cases. So you have already the formula with you. We have discussed this formula earlier. Once multipliers are with you, you can get MRX and MRY separately. That will be equivalent to MUX and MUY. So you have multiplier, no sway case for the no sway movements, sway multiplier for the sway movements. So similarly in Y direction. Bending strength, then you have to apply the checks. So after that you have MRX and MRY. So you have the capacities, bending strength capacities. So you can check it for phi B, M and Y. So you have the formula with you. Check conditions of the compact section as the beam. After this, all of the flow chart components or the steps are going to be involved. The beam checks. Okay, so for the compact section as the beam, you have to find out the LP and LR for the column tables, and you have to check against LBX. I'm not repeating it. This is chapter number 4 of your steel structure book, reference book by Dr. Zahid Ahmed Siddiqui. So you can go over there and you can again review the beam design and how you have applied the checks for that. So whatever you have applied over there, so keeping your column, considering your column as a beam, you are just using all of the same formula. So you have LBX, LP and LR with you. So use CB is equal to 1 in the expression, and you can get the capacity, and you can check your capacity for the capacity of the available section, trial section. Finally, to use the interaction equation, you have the condition PR over PC. If your PR over PC ratio is greater than 0.2, then you have to use the multiplier to reduce the contribution effect of the movements in the interaction equation. It will give you this answer. And if this ratio is less than 0.2, then you are going to be use this interaction equation. So you have to be very careful while selecting the interaction equation. Next step is that if you are getting your answer less than 1, greater than 1, so you have to revise in any case your section. But let's suppose if your answer is less than 1, but in less than 1, its category is like this, that your values of left hand side, when your answer of the interaction equation is between 0.9 and 1, what will be the comment you are giving at the end, or what will be the results? It will be very economical design. If the results of the interaction equation be between 0.8 to 0.9, it will be economical, average. If it will be 0.7 to 0.8, it may be acceptable, but better to try an economical section. If it is less than 0.7, you have to revise by a lighter section. And values of the left hand side, if it is greater than, of course, you have to select a stronger section. That is obvious. Now you have to check the shear strength, but if it will be an hot rolled W section, so we are avoiding and omitting this step because it is already going to be having a very highly shear strength available with the hot rolled W sections. So for that particular case, you are not going to be apply the shear check. So you have to write the final solution using the standard designation, that is the W, the depth into weight.